Okay, so let us now relate spans to solution sets of homogeneous equations. Now remember, that's exactly what a null space is. A null space is a solution set, for instance, for ax equal to 0, that's equal to the null space of A. So that's what we're doing, relating null space, which is a solution set, to a spanning set. The first theorem is here. Suppose that A is an n by n matrix, B is row equivalent in reduced row echelon form. Suppose B has R pivot columns where the indices are given by this. Now this should look familiar. We've had same type of structure in previous theorems, that we divide the columns into pivot columns and non-pivot columns. Pivot columns have indices D, non-pivot columns have indices F. We know that the last one is a, well, if we want a consistent system, then the last one must be a non-pivot column. Okay, and we construct the n minus r vector z in this way, and I'll say a little bit more about that later. Then the null space of A is given by the span of these vectors. So what's going on here? Let me go back to this theorem here. Now, what we just saw looks very familiar, looks very much like this. Now, if you remember this theorem said that to find a vector form of a solution to a linear system, you define a vector based on the constants here, and you define a vector based on the non-pivot columns here. And then you can write the solution as a sum of vectors. Now, in the case of a homogeneous system, this C is 0. So we have a 0 here. So if we have a homogeneous system, we do have our solution set as a linear combination of these vectors U. These vectors U were formed on the basis of the non-pivot columns of the reduced row echelon form of the matrix. Okay, so really this is just what we want to prove down here in another way. Okay, this is the same vectors. If you go, so I invite you to look at this form here. Go back to this theorem, look at the same thing. You have the same vectors. The only difference between this theorem and the previous theorem is that the previous theorem allows a non-homogeneous system. If you specialize this theorem to a homogeneous system, you get exactly this result. Okay, so that's, I'm not going to say any more about the proof. Here he goes through this formally, and I don't think it's necessary for me to say any more. Okay, so he does notice the difference between the two theorems. In the first case, you had an augmented matrix of an arbitrary linear system. In the latter, it's row-reduced version of the matrix, but this matrix is the corresponds to the augmented matrix of a homogeneous system. Remember, the homogeneous system, the augmented matrix only has last column of zeros that we can simply ignore, because when you reduce a augmented matrix if you reduce an augmented matrix whose last column is all zeros, then you know that the reduced matrix will also have a matrix form here, and the last column will still have all zeros. Okay, so these two are really very closely related, almost identical. All right, so here's an example of spanning set of a null space. Okay, now here we have a matrix A. Now this is not an augmented matrix. You should think of this as a matrix of coefficients. Okay. If you're going to think of the homogeneous system LS of A0, you would add an augmented column here. But as I said, we don't really need to, because we know that when we row reduce, that column will remain as zeros. Okay? So you should think, again, of this matrix as a matrix of coefficients. So just imagine a last column here that gives you the homogeneous system. So when you row reduce this matrix of coefficients, you'll get this result. And remember, you should just think of this being 0 here. And then these row-reduced rows give us equations. For instance, we have 1, 2, 3, 4, 5 variables. We have 2 free variables, x3 and x5. So we know that our solution is going to have 2 arbitrary constants. And here, for instance, I get x4 equals minus 3x5, etc., etc., etc. If you go through the procedure, you'll find out that your solution can be written in vector form as the linear combination of these 2 vectors. Okay? So here we have 2 vectors in the null space, such that any linear combination of those 2 vectors gives me all possible solutions of the null space. Right. Just to look ahead, this means that the null space has dimension 2. But we'll talk about that more later. Just thought I'd throw that out. Okay. So the null space is spanned by 2 vectors. Okay. All right, here's another example. Coefficient matrix, row reduce, 1, 2, 3 free variables. We're going to have 3 vectors to be the set of vectors that gives us the span. You go through the same procedure to find those 3 vectors, and you get the null space as the span of those 3 vectors. Okay. Okay, now let's use this to play around a little bit with the columns of the matrix. Here we have 4 vectors here. And you can use the same procedure to show that this vector is in fact a vector in the null space. It's a solution. You can check it by hand simply. If I look at, say, for instance, the first component, I get 2 times 2 is 4, plus 3 times 1 gives me 7, plus 0 times 7 gives me 0, plus 1 times minus 7 gives me 0. So the first component, when I apply these coefficients to these vectors, will give me a 0. I can do the same for all 3 components and verify that this is a solution to the homogeneous system. So I can actually write the linear combination of these vectors corresponding to these coefficients is going to give me the 0 vector. 2 times the first vector plus 3 times the second vector plus 0 times the third vector plus 1 times the fourth vector gives me the 0 vector. So that's what's written here. Now I can rearrange and express the fourth vector, W4, in terms of the other 2. So think about this. I can define the span of these 4 vectors, and I could write it as this. I could write the span of T as equal to the span of W1, W2, W3, W4. But I can actually write it in a simpler way, because anything in the span of these 4 vectors will also be in the span of the first 3 vectors. How do I know that? Because any linear combination that has W4 in it, I can replace that W4 with a combination of W1 and W2. As follows. Here's a linear combination of these 4 vectors. Now I know W4 is equal to minus 2W1 minus 3W2. So I can replace this W4 with minus 2W1 minus 3W2. When I do my vector operations, I know that minus 3 times minus 2W1 is 6W1. We can distribute minus 3 times minus 3W2 is going to be 9W2. That's where this comes from. And we know by the commutative properties and the distributive property that I can combine this with this and give me 11 W1. I can combine this with this and give me 5 W2. So I've written this combination of 4 vectors as a combination of the first 3. Okay? In other words, the span of all these vectors is in fact equal to the span of these 3. So I could write this span of these 3 vectors is actually equal to the span of the 4 vectors. I lose nothing by removing W4 from my set of basic vectors. Okay? All right, here's a similar example. Just the same thing with another set of vectors. Okay, so let's stop there.